Good day, viewers. I welcome you to today's class. Once again, my name is Dr. Chris Isekaide. I welcome you to today's class on analysis of variance, ANOVA, and the F distribution. Analysis of variance, ANOVA, and the F distribution. I hope you have been watching all my videos in my YouTube channel, Dr. Chris Isekaide. It is a channel designed to solve problems in statistics and mathematics. Quite a number of topics have been taught in that channel. Please visit the channel, subscribe to the channel, click on the notification button so that each time I upload a new video, you will have a notification. Share my videos in your social media platform. Click on the like button, like my videos, share them on your social media platform, and as you do, God will bless you. The essence of this YouTube channel is to share knowledge across the globe. Like we all know, mathematics and statistics are very important in all aspects of life. In every field of study, in knowledge in statistics or mathematics is required. And again, the channel is Dr. Chris Isekaide, and that is my name. I am a chief lecturer and also a member of the academic board in one of the most prestigious polytechnics in Nigeria. I hold a doctorate degree in mathematics with distinction, a master's degree in mathematics, and a bachelor degree in statistics. I've written quite a number of books in statistics and mathematics, and I have scholarly publications at national and international levels, and I've also presented papers in renowned conferences. I'm a member of the Nigerian Mathematical Society and also a member of the Nigerian Statistical Association. Here are my contacts. You can contact me for your research work. If peradventure you are a research firm or an AI institute or a research institute across the globe. I work in Nigeria, I live in Nigeria. I do my job in English language. I am fluent in English and I write English also very well. So you can contact me. Here are my contacts. +234 8033 021903. You have to put this code +234 if you are calling from outside Nigeria. And this first number is WhatsApp and it's also for call. Then the second number +234 7066 297535 is for call only. Then this is my email address, chrisdavid2015@gmail.com. I'll be looking forward to hearing from you. If you are an artificial intelligence firm or institute where you develop advanced mathematical algorithms or models or statistical algorithms or models for artificial intelligence and machine learning, I'll be glad to be part of your work. Or you are a research institute or you are a researcher, you want to consult me for your research work and analysis, why not contact me? I am a specialist in numerical analysis, data analysis and modeling, statistical analysis and scientific computing. Those are my areas. I've been teaching courses in mathematics and statistics across tertiary institutions in Nigeria over the past 20 years. So that is the wealth of experience I'm displaying in this YouTube channel. Click on the share button and share my videos and subscribe so that each time the video is uploaded, you will have a notification. Thank you. It is now time for us to go into the business of the day. Today we shall be looking at analysis of variance. That is the short form for analysis of variance is ANOVA and the F distribution. So we shall be looking at one-way ANOVA today. That's the simplest form of analysis of variance. Permit me to clean my contact. I believe you have taken note of the contacts. I'll be waiting, looking forward to hearing from you. And as you do, God will bless you. So let us go into the business of the day. Analysis of variance, ANOVA, and the F distribution. Like we all know, many statistical applications are done in various fields, like in business, in sciences, in engineering, in psychology, what have you. Statistical applications are done in quite a number of fields today. And this is what gives birth to what we call data science. And by so doing, by carrying out these statistical applications, many or several groups are involved. So it involves several groups. So for hypothesis test that involves the comparison of averages between more than two groups, statisticians have developed a method called the analysis of variance. The analysis of variance is a hypothesis test that is used to compare averages. So ANOVA, like it is called, ANOVA, which means analysis of variance, is for hypothesis testing. It is for hypothesis testing and also involves the comparison of averages. It is for hypothesis testing that involves comparing averages, between more than two groups. That is what we use analysis of variance for. ANOVA is for hypothesis testing that involves comparing averages between more than two groups. So statisticians, this ANOVA was developed by statisticians, and the simplest form of ANOVA is called the single factor or the one-way ANOVA. So you can also, this one-way ANOVA can also be called the single factor. So you can also call it the single factor. It's also called the one-way ANOVA. So the essence of ANOVA is to test hypotheses for comparing averages. When we talk about averages, means between more than two groups. So the groups must be more than two. It must be more than two. So ANOVA uses variances to determine if the means are equal or not. It uses variances to determine if the means of the groups are equal or not. So that is what ANOVA does. It uses variances. That's why the name is called analysis of variance. Then the F distribution is what ANOVA uses to test hypothesis. There is a test statistic we call the F test statistic, and that is what the analysis of variance uses to carry out this hypothesis test. So the F distribution is what the analysis of variance uses to carry out its test. So it uses variances to determine if the means of these various groups are equal or not. So statistical applications in various fields involves several groups that may be tested for comparison, similarities, and so on and so forth. So the analysis of variance is used for such a test. Now, assumptions to be satisfied before using the one-way ANOVA. So now we are going to the one-way ANOVA. We have the two-way ANOVA, the one-way ANOVA, and then we also have the one-way ANOVA is a randomized design. The two-way ANOVA is the completely randomized block design. We also have the Latin square design. We have the Greco-Latin square design. So we are looking at the one-way one-way ANOVA. That is a single factor ANOVA for today's class. That's the simplest of all. Like I said, the F distribution is what the analysis of variance uses to carry out test of hypothesis. Now, assumptions to be satisfied before using the one-way ANOVA. Assumptions to be met before using one-way ANOVA. The conditions, I'm going to highlight them so that it will be clearly understood. I will highlight them and explain them accordingly. Assumption number one is that each population from which a sample is drawn is assumed to be normal. So each population is assumed to be normal. I know we are making use of samples, so each population from which each sample is drawn is assumed to be normal. Then assumption number two, all samples are randomly selected and independent. So they are randomly selected. So all samples are randomly selected and independent. That's so there's no bias in selecting sample from a particular population. They are randomly selected and they are independent of each other. Then number three, the populations are assumed to have equal standard deviations. So the population are assumed to have equal standard deviations, or you can say variances, because the square root of the variance is the standard deviation. So the populations are assumed to have equal standard deviations. That means, or equal variances. Then assumption number four, the factor is a categorical variable. The factor is a categorical variable. So it is one variable that has categories. Just a variable that has categories when you are dealing with the one way. So it's just a variable that has various categories. That is what the one-way analysis of variance is. It's just a single factor. That's why it's called single factor or one-way analysis of variance, but it has categories. It has categories. Then assumption number 5, the response is a numerical variable. The response or responses, the response is a numerical variable. So hence the one-way analysis of variance or analysis of variance is a parametric test because it involves numerical variables. So numerical values are involved. So the data are quantitative, they are numerical in nature, they have numerical values, so they are analyzed using the parametric test, and the F test or the ANOVA test is a parametric test. That is what it means. The F test is a parametric test because the response is a numerical variable, and the responses are numerical, they have numerical values, hence can be analyzed or tested using a parametric test. And the analysis of variance is a very good example of the parametric test. Now these are the things we have. Now permit me to go into the nature of the hypothesis for the one-way analysis of variance. So for the one-way analysis of variance, permit me to clear this part of the board. It is good we understand the nature of hypothesis because analysis of variance involves test of hypothesis. And in our video, the last video we did on test of hypothesis, we highlighted the procedural steps for testing hypothesis. The procedural steps were highlighted for test of hypothesis. Now, the nature of the hypothesis, I will say hypothesis for one-way ANOVA. One-way ANOVA. It is good you know how to set your hypothesis. Analysis of variance is a parametric test, so it is good you know how to set. In our hypothesis test, we told us that we have two types of hypothesis: the HO and the H1. The HO is the null hypothesis, and it is the hypothesis that is given under the assumption that it is true. Then the H1 or the HA is the alternative hypothesis. The alternative hypothesis contradicts, opposes, or complements the null hypothesis. So if we are to set this, the null hypothesis will tell us that all groups have equal population means. That's what HO will tell us. All groups have equal population means. That means the means of the various groups, the population means of the various groups, they are equal. That is what it means. That means in normal sense, that means the mean population mean of the first group is equal to the population mean of the second group, is equal to the population mean of the third group, and is equal to the population mean of the kth group if the groups have k number, or there's a k number of groups. So that is what HO tells us. The population or all groups have equal population means. That is what HO tells us, because we are testing for equality of means using variances. That is what it does. So the alternative hypothesis H1 will contradict that. H1 will say at least two group means are not equal. This one will say at least two group means are not equal. That is also, it's contradictory. This one is saying all the population means are equal. That's what HO is saying. That means the mean, mu means population mean. In statistics, when you talk about mu, when you see mu like this, it's called the population mean. That is what mu means. So it is the population mean. So mu1 means the mean, the population mean of the first group. Mu2 means the population mean of the second group. So since it involves a single factor, and the factor is a categorical variable, and the response or responses from these factors, they are numerical. So each factor or each group from the variable has a population mean, because the sample is drawn, the sample is drawn from a particular population. So the population or the populations that produced the various samples are assumed to have equal standard deviation and variances, and they are also assumed to be normally distributed, and the samples themselves must be randomly selected, and they must be independent. So by implication, it means that our H1 will now be that our mu I is not equal to mu j. That is what it means. For some I greater than j, for some I not greater than or equal to j. That is what it means. So it simply means that at least two of the groups don't have the same mean, the same population mean. That is what it means. Now, the distribution used for the hypothesis test is called the F distribution. So the distribution used for testing hypothesis, the distribution used for hypothesis test is called the F distribution. So the F distribution is what is used to test hypotheses for analysis of variance. So, and this F distribution is named the F distribution is named after an English statistician, Sir Roland Fisher. Is named after Sir Ronald Fisher. So that is the father of an analysis of variance test. This Sir Ronald Fisher was an English statistician. He was an English statistician. An English statistician. So now, the F, this will now produce what we call the F statistic. The F statistic is a ratio, and it has two sets of degrees of freedom. It is a ratio, and it has two sets of degrees of freedom. The F statistic is a ratio, and it has, so the F statistic is a ratio with two degrees of freedom. degrees of freedom. That is what the F statistic is. So the values of the F distribution are squares of corresponding values of the T distribution. So the one-way ANOVA expands the t-test for comparing more than two groups. You can see now the one-way analysis of variance is an expansion of the student t-test. It is an expansion of the student t-test. That is what the one-way. The student t-test is primarily used for testing two groups, but when it involves more than two groups, we make use of the one-way analysis of variance. It is preferable to use ANOVA. It is preferable to use analysis of variance when there are more than two groups, instead of performing a pairwise t-test, because performing multiple tests or a pairwise t-test will introduce the likelihood of making a type 1 error. It will involve the likelihood of making a type 1 error. Now, to calculate the F ratio, two estimates are made. Permit me to go to that. When calculating the F ratio, two estimates are made. When calculating the F ratio, two estimates are made. Let us look at those two estimates before we go into the format, the one-way analysis of variance format for the F test. So now, to calculate F ratio, two estimates are made. The first one is the variance between samples. You estimate the variance between samples. When we talk about the variance between samples, this is the variance or the variation due to treatment, or we call it explained variation. Explained variation. So it is the explained. When you estimate the variance between samples, then you are doing what we call the explained variation. Then the second estimate that is done is variance within samples. Variance within samples. And this variance within samples simply means the variation due to error. It means variation due to errors, variation due to error, or unexplained variation, or unexplained variation. So the error, so that there's always a room for error in hypothesis testing, especially when you are dealing with analysis of variance. So there's a room for that. So the variance between sample has to do with the variation, the explained variation, while the variance within sample has to deal with the variation due to error or explained variation. Now, permit me to go to the one-way and to write out the one-way ANOVA format. Permit me to clean this, the one-way ANOVA format. There is a format for the one-way analysis of variance. There is a table, because these things are put in tables and it is easy to analyze. So the one-way ANOVA format, the one-way ONE-WAY ANOVA formats. So let us look at it. So it starts with what we call the sources of variation. Then number 2, the degrees of freedom. Then we have the sums of square. The degrees of freedom is df. The sum of square is ss. Then we have the mean sum of squares, and this one is ms, mx, and then finally we have the f ratio. So the f ratio is the final one, the f statistic. So this is the f ratio. Now this is how we are going to do it. We are going to roll the line. Please take note of this, is very important. We take note of how this is calculated, and so on and so forth. So now under the source under the source of variation, we have the factor or treatment. We have factor, and this one is between the samples. Then it has k minus 1 degrees of freedom. K is the number of groups. K represents the number of different groups. Then the sum of square is called the S factor. That's what the sum of square is called. Then the mean sum of square, it means the ms factor, like that. Then the second source of variation is the error. And error is within. Now we talked about the variance between the samples. That is the first one, that is the factor. Then we talk about two estimates to be done. The first one is the variance between the samples. The second one is the variance within the sample. The variance within the sample is the error. Then the variance within the sample, or the sum of square, or the error, has degrees of freedom n minus k. N is the total number of observations. N is the total number of observations, or all total number of values. Then, of course, here we have the sum of squares for the error, or some will say sum of square within. Then we have for this one, this is equal to, if you want to calculate this will be S factor all over k minus 1. Permit me to take this a little down. Permit me to take it a little down. So the formula for calculating that, you divide, for you to get the mean sum of square for factor, you divide the sum of square for factor by the degrees of freedom k minus 1. Then the second one is error, and that one is within. Then you put it in bracket, it has n minus k degrees of freedom, and it is called sum of square is called ss error. You put it in bracket. Then the main sum of square for it, is ss error divided by its corresponding degrees of freedom n minus k. That is what it has. So now, then our F ratio will be equal to the mean sum of square for factor all over the mean sum of square for error. Then of course there is also what we call the total sum of square. We have for the total sum of square is n minus 1. When you add these two degrees of freedom, you have n minus 1. Then for the sum of square for the total, we call it SS total in bracket. So that is where we stop for the total. So you see this is the ANOVA format for the one-way analysis of variance. It is the ANOVA format, the format for the one-way analysis of variance. You take note of this, you have the degrees of freedom, you have the sources of variation. We have two sources because two estimates are involved. The variance between samples, that is the one between them. Then we have the variance within sample, that is the error, that is the variation due to error, and or the unexplained variation. Then it has its degree of freedom to be n minus k. K is the number of groups, n is the total number of observation, and so on and so forth. So permit me to kind this format so that we can see the various formulas. So now, permit me, you have taken note of this format. We are going to apply it as we progress. By the time we pick a particular example and solve that example, you will see how this particular format is applied. So note that our K is the number of groups, and again our Mj is the sample size of the jth group, size of jth group J or the jth group, and again we have our Sj. This means the sum of the values in jth group, sum of the values in jth group. And again we have what we call the correction factor, which is CF, and that is equal to, the CF is summation x all squared all over n, or you can call it summation xj all over n, summation sj all squared all over n. That is what the correction factor is. Then of course we need to see how the sum of squares between is calculated. So SS between is equal to the SS, the formula for the SS between is equal to summation Sj squared all squared all over Nj minus Cf, which is the correction factor. Then the SS total is equal to summation x squared minus the correction factor. So the correction factor will be calculated first. So the summation, you sum each value, you take the square of each value and sum it, and you subtract the whole sum, you subtract the correction factor from the whole sum to get the SX total. Then of course our n, which is the number of observation our n is given as summation n pi, I is equals to 1 to k, so it's going to be n1 plus n2 plus n3 plus nk. That is what our n is. So you sum this the number of sizes in each group to get n. So that is what our n is. So now you must also understand that our SS total, that is the sum of square for the total, is equal to the SS between plus SS error. So when we are able to calculate the sum of square for between the sample and the sum of square for the total, we subtract that of sum of square between from total to get that of error. So directly we are saying that our SS error will be equal to XS total minus XX between. By simple arithmetic, that is what it means. So you will see that this thing is very easy to carry out. It's very easy to carry. Now, the best way of explaining this thing is by solving a practical example. So permit me to clean this part of the board as we take a practical example that involves one-way analysis of variance. Note, the F distribution is used to test hypotheses for the one-way analysis of variance. Now, let us take a practical example. 10 chickens were given one of 3 different diets. 10 chickens were given one of 3 different diets. We are given one of 3 different diets. One of 3 different diets, and their body weight recorded in the table below, and their body weights recorded. Their body weights were recorded in the table below. Test at 5%. Test at alpha is equal to 5%. At alpha equals to 5% if there is a significant difference among the diets. Or say for significant difference among the diets. So that is the question. Now the table is given below. We have the diets, and the diets are 3. So we have diet 1, diet 2, and diet 3. Under diet 1, we have 5, we have 4.5, we have 4, and we have 3. Then under diet 2, we have 3.5, we have 7, and we have 4.5. Under diet 3, we have 8, we have 4, and we have 3.5. So it is good we take the totals. Now, taking the total from diet 1, these are the weights. And we are told that the chickens are 10. So let's count 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. So let's take the total for the weights from each diet. The first one, if you sum this, is 16.5. If you sum the second one, you're going to have 15, 3.5 plus 7 plus 4.5, you have 15. Then the third one, 8 plus 4 plus 3.5. If you sum it, you are going to get 15.5. So this is the sum of the weights recorded from the chickens, that the sum of the weights of chicken that fed from diet 1 is 16.5. The sum of the weight of the chickens that fed from diet 2 is 15. The sum of the weight of chickens that fed from diet 3 is 15.5. Now, let us bring out the necessary ingredients. From here, you will notice that our key is equal to 3 because the number of groups. You can see now the variable or the factor is a categorical variable. It has one factor, it's a single factor. It's one-way ANOVA, analysis of variance. That single factor here is diet. Then it has what we call numerical responses. The responses are numerical. Now look at the weights, they are numerical. So that this is what makes the analysis of variance test a parametric test. The weights are numerical. You see, the diet is a single factor, but it has 3 groups. One factor having 3 groups. We said the variable must have more than 2 groups. So it is used to test for more than 2 groups. So the hypothesis testing involves comparing averages between more than 2 groups. That is also, here the groups are 3, but it's a single factor, and that factor is diet. So the number of groups we have here now is 3. And you will understand that this simply means that our N1, that is the sample size of the first group, 1, 2, 3, 4. Our N1 is 4. Then our N2, the sample size of the second group is 1, 2, 3 is 3. Then the sample size of the third group is also 3. That is N3 is equal to 3. You have that. Then it will also interest you to know that we have the sum. So the sum, X represents the sum. The sum of the first group is 16.5. The sum of the second group is 15. The sum of the third group is 15.5. And this will now lead us to our N. Our N is N1 plus N2 plus N3, and that will be equal to the size of the first one of the first group is 4. So this will be 4 plus 3. The second group is 3. The third group is 3. So our N will be equal to 10. This is how you bring out the various ingredients for your analysis. Our K is 3, the number of groups, and so on and so forth. So now you will permit me to start by solving. So solution now. Our first step is step 1. We have to state the null hypothesis. HO simply means there is no significant difference among the 3 diets. That means the 3 diets have equal means. No significant difference among the 3 diets. That means they have equal means. That means mu1 is equal to mu2 is equal to mu3. That is what it means. they have equal means. Then the alternative hypothesis H1, that's why we tell you that there is significance difference among the diets. That is what H1 will tell you. That means the means, not all the means are equal. It simply means, this one is saying not all the means are equal. That is what the H1, the alternative hypothesis, is telling us. So, having gathered this information or these facts from this particular problem, it is good we go ahead to calculate our correction factor and the sum of square for between, and the sum of square for error, and the sum of square for total, and so on and so forth. So now we are going to have, now it means that from here our summation x squared will be the sum of each of these. So permit me to claim the question. I hope you are taking the question. Permit me to claim the question so that we can start carrying out our calculation of sum of square for between and sum of square for within, like the sum of square for error. So I hope you have taken note of all the necessary facts we have been able to bring out, and then take note of these hypotheses. Now, the step 2, we want to calculate the sums of square. So step 2, calculate the sums of squares. So the first one we are calculating is our correction factor. So our correction factor, our CF, is equal to summation x all squared all over n. I see it as summation sj all squared all over n. Now that means we have, this is x1, x2 and x3. So this will now be equal to 16.5 plus 15 plus 15.5 all squared all over our n, remember, is 10. So our n is 10. 4 plus 3 and that is 10. So having that, our CF, correction factor, will be equal to, when you sum that and you square it, you are going to have 2209 all over 10, and that is equal to 220.9. That is our correction factor. Now, permit me to claim the step 1, which is the hypothesis, so that we can continue to calculate our sum of square. So the next one is to get the sum of square for the factor. So we have SS factor. Remember, the factor is diet. Some authors can decide to say SS diet. So I can permit me to put it SS diet. It's a single factor, and that factor is diet. So the sum of square for diet is equal to summation x j squared all over n j minus the correction factor. So our S diet will be equal to, now we are now taking each of them. The first sum is 16.5. It will be 16.5 squared all over what is the size of that first sum is 4. The sample size is n is the sample size for the j's group 1, 2, 3, 4. So all over 4. We put a big bracket here plus. Then the second one, because j run from 1 to 3 is 15. So this will be 15 squared because you must square it, plus 15 squared all over. The size of it is 3. Plus the next one is 15.5 plus 15.5 squared. Let me close this bracket. Then the sample size is 3. Then you cover the bracket minus our CF is 220.9. That is what you have there. So if you are going to have that, you are going to have your SS diet. You carry out this, you are going to have a total of 223.1458, 223.1458, 223.1458 minus the correction factor 220.9, and that is equal to the SS diet will be 2.2458. 2.2458. That's our SS diet. Now we'll come again and get our SS total. Our SS total will be equal to summation x squared minus CF, and this is how it goes. Now when you talk about x, you are talking about each of these. So you are going to have the first value of x is 5, the various values. So this will be 5 squared plus 4.5 squared plus 4 squared plus 3 squared plus 3.5 squared plus 7 squared plus 4.5 squared, like that. So I think the 10 of them, that's what it's called the sum of square, plus 8 squared plus 4 squared plus 3.5 squared. You close the bracket. That is what this x squared means. 5 squared plus 4.5 squared plus 4 squared plus 3 squared plus 3.5 squared plus 7 squared plus 4.5 squared plus 8 squared plus 4 squared plus 3. You take it like that. That is what the summation f of summation x squared means. Then our CF, which is the correction factor, minus CF, that is 220.9. So carrying that out, our SS total will not be equal to, when you carry out this calculation, this summation S, which is the one in bracket there, you are going to have 244. So you are going to have 244 minus the correction factor 220.9. So carrying that out, 244 minus 220.9, you have 23.1. 23.1. So our sum of squares for total is 23.1. Now it is good we get our SS. Remember our SS total error, which is the SS within, is equal to the sum of square for total minus sum of square for diet. That's what you have. So our sum of square for total is 23.1 minus sum of square for diet is 2.2458. When you carry out that little arithmetic, you are going to have 20.8542. So you are going to have 20.8542. So that will now be our sum of squares for error. That will now be our sum of squares for error. So we have been able to compute step 2. Step 2, we have calculated all the sum of squares for error, sum of squares for diet, which is the sum of square for factor, then the sum of square for error, which is the sum of square for within. So, beloved, I want to also play with you. Please subscribe to my YouTube channel, Dr. Chris Esekaibe. Click on the notification button, subscribe to my channel, please, so that anytime I upload a video, you will have a notification. Share my videos in your social media platform, like my videos, and if there is any comment, please put it in the comment section so that I will be able to know what I am doing, so I'll be able to at least see how I am impacting others. And if there is any topic you really want me to teach that has not been taught, you can also put it in the comment section and it will be attended to. Quite a number of persons have been asking questions from the comment section and I've been attending to their questions. If you are also a research student, you can meet me. Somebody sent me a WhatsApp message from Rwanda saying that she is an MSc student in mathematics, and her area of specialization is numerical analysis, and she was attended to. Why not, if there is any thing you want us to do, you can be a research firm or a research institute, or you deal on artificial intelligence, we can work together and do mathematical models and algorithms. I will be looking forward to hearing from you. You will see my contacts in the description part of my channel, where the channel was described. You will see my contact and my email. Even at the beginning of each of my video, you will see my contact and my email address there. I will be looking forward to hearing from you. So our sum of square for error is 20.8542. 20.8542. So, and now we have done the first two steps. The first step, we stated the null alternative hypothesis. The second step, we calculated the sum of squares. Now permit me to go to the next step. That next step is the construction of the analysis of variance table. Please permit me to clean all these, take note of them, make sure you are writing them down, take note of them. So take note of all the values. We are going to use them to construct our analysis of variance table. So that is what we want to do now. Construction, that is step 3. Step 3, construct the ANOVA table. So step 3, construct the one-way ANOVA analysis of variance table. So that is the third step. So now, when we say XV, you are not new to it. It's our source of variation. Then our DF is our degrees of freedom. Then our SS is our sum of square, and our MS mean sum of square, and our F ratio. Now let us go ahead and do the needful. The first source of variation there is the factor, and the factor, the single factor, the diets. So you put it in bracket. But from the format we shared, the degrees of freedom for diet is K, for factor is K minus 1, and of course our K is 3, the groups are 3, it will be 3 minus 1, and that is equal to 2. So we have that. Then of course we calculated the sum of square for diet. SS diet is equal to, sum of square for diet is 2.2458. 2.2458. Then the main sum of square for diet will now be, you are dividing it with the corresponding degrees of freedom. So it will be this 2.2458 all over the corresponding degrees of freedom 2, and that will be equal to, when you carry out that calculation, you are going to have 1.1229. 1.1229. Then you have that. I'm waiting for our F ratio. Then permit me to share this way. Then the next one is for error. The sum of square for error, and our error is n minus k. Remember, our n is 10. So this will be 10 minus k is 3. The groups are 3. The single factor, the factor is diet having 3 groups. 10 minus 3, that will be 7. Then our SS error, sum of square for error will now be equal to 20.8542. 20.8542. Then of course we have another one here for total. Our total is n minus 1, and that is equal to 10 minus 1 is equal to 9. So look at it here now. 10 minus 1 is 9. If you add these two, you get the total. 2 plus 7 is 9. N minus 1, n is 10. That is the sum of all the values. Then now our SS total, our SS total will be equal to, of course, if you add these two together, you will get our SS total, and our SS total is 23.1. 23.1. That is what the value for our SS total is. Now we'll go for the sum of square for error. Now you are dividing we are going to the mean sum of square for error. You are dividing the sum of square by the corresponding degrees of freedom. So this will be 20.8542 over 7. And that will be equal to, when you divide that by 7, you are going to have 2.9792. 2.9792. And of course, we don't need to have the mean sum of square for total. Then our F ratio, remember, our F ratio is equal to mean sum of square for diet all over mean sum of square for error. So that will be F, we call it F will now be equal to the mean sum of square for diet is 1.1229 all over, then the mean sum of square for error is 2.9792. So our F calculated will now be equal to 0.3769. 0.3769. So that is the value of our calculated F. So now this will now take us to the table value of X. Remember, our table value, now the step 4, get the table value. So we use the degrees of freedom. Now how do we get that? Now we are going to get our F. Remember, we are testing at 5%, 0.05. Then we are using 2 degrees of freedom. Remember, the F ratio is with 2 degrees of freedom. So the first one is the one from the diet, and the second one is the one from the error. So 2,7. So what you need to do, you need to go and check the analysis of variance table for 5%. We have the analysis of variance table for 1%, for 5%, for 2%. So you will trace the one for 5%, then you will now check 2 under 7. I repeat, you check 2 under 7. The value you are going to get is 4.74. That's what you are going to have, 4.74. So our table value will now be 4.74. That is what we are going to have. So it is good. That is something you also need to know, that the estimated population variance. The estimated population variance is equal to, note that the estimated population variance is mean sum of square for error, and that is equal to, the mean sum of square for error is 2.9792. So this is the estimated population variance for this particular test. The estimated population variance, so is the anytime you carry out analysis of variance, you construct analysis of variance table, the mean sum of square for, there's always a row for column. The mean sum of square for error is always the estimated population variance, and it is the value that we have here, 2.9792. So please take note of that. And again, you need to understand that the mean sum of square within is the estimate of the population variance that we said, while the mean sum of square for the factor, which is for between, consists of the population variance plus a variance that is produced from the differences between the samples. Now let us go to step 5. Step 5 involves taking decision and conclusion. Take a decision and conclude. Now, you know, the decision rule says if f cal is greater than f tab, comma, you reject HO and accept H1. Now, you will agree with me that here, our HO, you can see that since since F cal is now less than F tab, comma, that is, what is our F cal? F calculated is 0.3769, is now less than our table value of 4.74. We are now going to accept HO. We accept HO and conclude that there is no significant difference among the 3 diets, and conclude that there is no significant difference among the 3 diets. This simply means that mu1, so by implication, it simply means that our mu1 is equal to our mu2 and is equal to our mu3. So the 3 means are the same. Since HO is accepted, that is the end of the test. Beloved, we have come to the end of one-way analysis of variance using the F-test statistic, using the F ratio or the F distribution. The F distribution is what we use to test hypothesis in analysis of variance, and we have been able to get the value for the F table, and we have compared it, and you can see that the calculated value, the calculated F, which is the F ratio, is 0.3769. The table value is 4.74. So the F calculated is less than the F tabulated, and when it is like that, you accept the null hypothesis, and you now conclude with what the null hypothesis says. I hope you have learned something today, beloved. It is good having you in my class today. Once again, subscribe to my YouTube channel, Dr. Chris Esekaibe. Click on the notification button so that each time I upload a video, you will have a notification. Like my videos, share them in your social media platform, and as you do, God will bless you. I'll be coming up again in my next video. I'll be coming up with two-way analysis of variance, or you can call it the completely randomized block design. It's used for completely randomized block design. This one-way ANOVA is used for the complete randomized design. The one-way ANOVA is a single factor. The problem we consider today, the single factor, is diets. Diets having 3 groups: diet 1, diet 2, diet 3, and they were administered on 10 chickens. And at the end of the day, we were able to analyze that these 3 diets are the same. By the test we have done, the 3 diets are the same. There's no difference among the 3 diets. They are the same, and it means that the test is concluded. Thanks for watching, for waiting patiently to the end of this video. God bless you. See you in my next class. Bye.